Hi guys, this is going to be the video lecture of properties of waves and wave interference, and let's get started. Alright, let's start with the definition of wave. What is a wave? It's basically a disturbance that's transferring the energy through the matter, and when it's transferring that energy, it's not displacing the material. And we have two main types of waves. One of them is mechanical, the other is electromagnetic wave. What makes it electromagnetic wave? What's the main difference in between them? Electromagnetic waves can transfer the energy through a medium and empty space. So what is a medium? It's the material through which a disturbance travels. So for example here, energy is traveling through the air. So air is my medium. So in the guitar, energy is transferring through the string. So the string is going to be my medium. And in water, energy is transferred through water, so water is my medium. So that's the definition of medium. And electromagnetic waves doesn't need any material to transfer the energy through, so they can also go through empty space. And the electromagnetic waves that we know of are radio waves, microwaves, infrared, visible lights, ultra waves, X-rays, and gamma rays. And all of the electromagnetic waves are traveling with the speed of light. Alright, so what's mechanical wave? What makes it mechanical? They are not able to travel through space, or they're going to need a medium to transfer the energy. And what are the mechanical waves that we know? Sound waves. So sound is not able to travel if there's no air or if there's no medium to travel through. So in space we have no sound technically, or sound doesn't travel through space. And water waves, they also need a medium. They can't really travel through space. And stadium waves, you need people to create that. And mechanical waves also have two types, transverse and longitudinal. And what's the difference in between them? So in transverse waves, the disturbance is going to have one direction. So here it is up and down. And when you create that disturbance, the wave is basically going straight. So the angle in between those two directions is 90 degrees. So when they're perpendicular, the disturbance and the movement of the wave, it's called transverse wave. And when it's called longitudinal, if the disturbance and the wave direction are parallel to one another, then it's becoming longitudinal wave. And sound waves are longitudinal waves because sound is traveling like this in the air. And what are the parts of the wave? Crest, trough, compression, rarefaction. So what are they? So crest is the top point of the transverse wave, and the corresponding name for longitudinal wave is compression. So compression is when the wave is basically most dense. And trough is the lowest points on a transverse wave, and in a longitudinal wave we call it rarefaction, and rarefaction is when the wave is less dense, so the separation is the maximum. Alright, what's wavelength? This is going to be an important one. It's the minimum distance between any two identical points. So for example, so crest to crest or trough to trough, this is going to be the wavelength, and it's shown with the lambda Greek letter, and most of the time we write it like this. And it's measured in meters because it literally measures the distance. So what is basically this wavelength? It's the displacement of the exact same point. So this point comes from this location to this location, but the displacement, the distance that it travels in the x-axis is by this much. So this is basically the repeating pattern, and the displacement of that repeating pattern is the wavelength of it, and it's basically lambda. Alright, so how do we find the speed of a wave? It's actually not really different than the regular speed, because if you remember speed in general, it's distance over time. So how much distance that you travel in a given time. So for wavelength, we said the displacement of one point from one location to another, or a wave, it's basically traveling like this. So two exact points, the distance from one to another, how much it displaced. This is given by wavelength. And the period is giving you the time of that cycle, because this is the length of the repeating pattern, and time for that repeating pattern is given by the period. So if you divide the distance by the time, which is wavelength divided by period, that's going to be the speed of the wave. But in waves, we have an alternative for period. And period is equal to actually 1 over frequency. But here, period is in the bottom, so it is basically wavelength times 1 over period. Then 1 over period can be replaced with frequency. Then my final answer, or my final equation, becomes as frequency times lambda. So if you multiply wavelength of a wave with its frequency, then it's going to tell you the speed of that wave. And speed of a wave depends on one thing only. This is very, very, very important. So it doesn't depend on the length, the wavelength. It doesn't depend on the frequency. So again, the speed is frequency times lambda. However, speed doesn't depend on frequency or the length of the wave. It only depends on one thing, medium. So it's like, how fast can a car go? What does it depend on? It doesn't depend on the length that it goes. It doesn't depend on how many cycles it makes. It actually depends on one thing. It depends on the engine of the car. So engine in that case for our wave is the medium. So how fast can you run in the air? How fast can you run in the water? If you change the medium that you have around you, that's going to change the wave. That's going to change the speed. So just like that, speed of a wave depends on medium. But in that equation, frequency also depending on one thing. Frequency depends on the source. So if you change the source, then you will be able to actually change the frequency of it. So considering those two ideas, then we can come over here and then look at this statement. If frequency increases, then the wavelength gets shorter. So how do we change the frequency? Basically the source. So to be able to create those three different waves, and let's say we are making those measurements, or we are making those waves, then to be able to create more frequent, and if you're using, let's say you have your a string in your hand and then you want to create those three shapes. So to be able to do this, you just need to shake it faster. But if you would like to do this, you go slower. So as you can see, your hand is the source, and then you can make it faster or slower, and that's going to change how many times you actually repeat yourself, or how many times you're going to repeat the wave. So frequency can be changed because it's in your hand, and your hand is the source. But once you change that speed, what happens? The speed of the movement, not the speed of the wave. As you can see, this is more frequent, and the length in between two crests is short. But if you have less repeating, so a little bit slower motion, then your wavelength is more. And if you have the last one, which probably the slowest movement, then your wavelength is the maximum. So as you can see, once you change the frequency, it is directly changing the wavelength. And what is the reason for this? Again, velocity is equal to frequency times wavelength, and frequency is changing. But to be able to change your velocity, you need to change the medium. So it's the same string. Medium is not changing. So to be able to keep this guy the same, increasing this guy is going to directly decrease the wavelength, or vice versa. If you decrease the frequency, then your wavelength will increase. So your velocity will stay the same because your medium is the same. So if you would like to change the speed, then how can you change the medium? So you can basically change the material, the string type, or the tension on the string, or the thickness of the string. So they are basically changing the type of the medium, and that's how you change the velocity of the wave. All right, that's going to be an important point for the later on conception questions, so that's why I want to stress on this. All right, what's wave interference? Waves are a little bit different than particles. So particles cannot occupy the same spot. So if you have, let's say, one block, and if you would like to put another block on it, then you can't really like occupy the same spot. That's not possible. So, but waves can actually share the same spot at the same time. So here, which wave is here? Once you ask that question, you can't really answer that because both of them are in the same location. So they are still there, so that when you have two different waves or more sharing the same spot, that's basically known as interference. All right, so to be able to know the rules of interference, we need to look at two things. One of them is going to be the reflection of a wave from a fixed end. So let's say you have a pulse and then you send it to a fixed end. And once you observe it, and actually let's do this. So this is our fixed end and I am going to create a pulse. So let's see what happens. So it goes and then it comes back. But when it comes back, as you can see, it was actually going positive direction, but then it is going negative direction. So whenever it actually hits to a fixed end, it flips. And one thing that you need to notice, the only thing that is changing is the sign of the amplitude. So it's positive and negative, and positive, negative. So nothing else is changing. It's still going with the same speed, still same frequency, same amplitude, same wavelength, everything stays the same. The only thing that is changing is basically the sign of the amplitude. And this is due to basically Newton's third law, because action and reaction, it basically tries to go up, but it's pushing it up, but it's not able to because it's fixed. So reaction, it basically flips it. All right, if you have a loose end, let's see what happens if you have a loose end. So this time there's nothing to react. So, but however, this end is still fixed, so this is going to have the reflection. But if you have this loose end only, it's not going to change anything. It will also keep the direction of the sign of the amplitude the same. So that is what happens once you have a reflection from a fixed and loose end. So how do we use, or what is going to happen once we know those two? So constructive interference and destructive interference. We're going to have two more terms that we need to know. So what is constructive and destructive interference? So constructive is once you have two waves, it doesn't matter what amplitude they have, but the key thing is they are going to have the same sign of the amplitudes. So in this case, they both are positive. So if you were talking about this, that would also create the same scenario. So what happens once they actually interfere, once they are in the same location, they are going to increase their amplitudes with the sum of them. All right, so, and if we were talking about this, if they interfere, what would be the shape of that? So basically that would increase the wavelength, the amplitude to the sum of the amplitudes. But that would just be negative. All right, so it doesn't have to be positive. The idea, to be able to constructive, you just need to have two waves with the same amplitude. And the interesting thing about that, they are not actually colliding and reflecting back. They are actually going through each other. All right, so as you can see, this wave is continuing with the previous, whatever it was initially, and the other wave is also going with the initial condition. So nothing is changing. After the interference, they still have the same amplitude, speed, frequency, and wavelength. Nothing is changing. So what is destructive interference? Basically, when you have two amplitudes with different signs, so one positive, the other is negative, and the amplitude principle is, or interference principle is still the same, you are still adding the amplitudes. However, since one of them is positive, the other is negative, when you add them, you're going to have basically the difference of those two numbers, but after the interference, they are just going to continue with what they have before. All right, so and actually, if two waves are having the same amplitudes, let's say one is going to have this and the other is going to have this, so they have same amplitudes. So when they interfere, they're going to basically create a straight line. And that's going to be a complete destruction or cancellation. So if you would like to see this, so let's create this. That was a little bit, all right, let's have a slow-mo. All right, so one of them is positive, the other is negative with the same amplitude. Let's see what happens if they continue. So they're interfering, and as you can see, for one moment, they are basically canceling each other out. So that is basically complete cancellation. But of course, this is a continuous thing, so they're going to continue to the motion. And if they interfere constructive, then they're just going to double the amplitude. All right, so that's basically what destructive interference is. And the last thing is superposition. So adding the amplitudes is basically superposition. So if you have one unit of positive and one unit of another positive, they're coming towards each other, then when they interfere, they're basically going to create two units of amplitude. So this is the superposition of those two waves. If you have one positive, two negative, when they interfere, what's going to happen? 1 plus minus 2, that is basically going to create -1, so that is going to be the interference pattern for you. So this is the superposition of those two waves. And what's going to happen if you have two different shapes, not the similar shapes? Then in this case, the idea is you're going to basically draw both of them at the same location, and those dotted lines are basically going to be the two waves in the same location. And the superposition is basically adding the amplitudes throughout. So if you look at this, this is going to have throughout, it's going to have basically 1 unit of amplitude. But this guy is going to start with 0, -1, and 0 again. So once you add 0 and 1, what do you get? 0 plus 1, it's 1. So once you are in the middle, this is still 1, this is -1. Plus 1, -1, it gives you 0. Plus 1, 0, it's 1. So your amplitude is basically, or your interference, your superposition is going to seem like this. So this is the basically superposition of those two waves. So you're basically adding all of the amplitudes throughout. And what happens after the interference? They are still continuing with the initial condition. Nothing is changing. No amplitude, speed, or wavelength, or frequency is changing after the interference. All right, so that's it for properties of waves and interference. See you in the next video.